Today's class is Doppler effect. In today's class, we study about Doppler. In this class, we study about what is Doppler effect, how it is produced, when there will be a change in wavelength lambda, what is the effect of the motion of the medium. Can we derive a formula for explaining this effect? What are the uses of this effect? These are the concepts which we are going to study in this class. Doppler effect. Doppler effect. It is the change in frequency noticed by an observer. It is the change in frequency noticed by an observer. Let us consider a whistling rail engine. Let us consider a rail engine blowing its whistle. For a passenger at rest on the platform, he receives the same frequency emitted by the engine. But if the passenger runs towards the engine, he notices that he is receiving greater frequency. If the passenger is running away from the engine, he will notice that he receives less frequency. The frequency of sound received by the passenger depends whether he is stationary or moves towards the engine or away from the engine. Same effect is noticed when the passenger is at rest and the engine is in motion. The whistling rail engine, if it is at rest, for the passenger at rest, the frequency will be the same. If the rail engine is coming towards the passenger, that is called as approaching, then the frequency of sound noticed will be greater than the frequency emitted by it. The frequency noticed by the observer is more if the engine is approaching, whistling engine is approaching. If the whistling engine is receding, then the frequency of sound noticed by the observer will be less than the frequency emitted by the whistling engine. This is known as Doppler effect. The change in frequency noticed by the observer is known as Doppler effect. We can define Doppler effect as the apparent change in frequency of sound noticed by an observer due to the relative motion between the source and the observer. We can define like this: the apparent change in frequency of sound noticed by an observer due to the relative motion between the source and observer is called. The following symbols are used in Doppler effect. V stands for speed of sound, N stands for frequency of sound emitted by the source, and lambda wavelength of the sound wave. Vs is used to symbolize the speed of source, and Vo the speed of observer, W the speed of wind. Lambda prime and lambda double prime are used for the modified wavelengths of the sound wave. N prime and N double prime are the apparent frequencies noticed by the observer. These are the symbols used in Doppler effect. Just we learned that the observed frequency is less or more depending on the motion of the observer and the source. Let us take mathematical relations that are used in calculating these frequencies. If the source is approaching a stationary observer, the relation for finding the apparent frequency is n prime is equal to V divided by V minus Vs into n. N prime is equal to V divided by V minus Vs whole multiplied by n. This is the relation used for the source approaching. If the source is receding from a stationary observer, the relation used for calculating the apparent frequency is n prime is equal to V divided by V plus Vs whole multiplied by n. N prime is equal to V divided by V plus Vs whole multiplied by n. If the observer is approaching a stationary source, the relation for apparent frequency is n prime is equal to V plus V naught by V plus V naught divided by V whole multiplied by n. If the observer is approaching, the relation is n prime is equal to V plus V naught divided by V whole multiplied by n. If the observer is receding from a stationary source, then the relation for apparent frequency is n prime is equal to V minus V naught by V minus V naught divided by V whole multiplied by n. So V minus V naught by V whole multiplied by n is the relation for apparent frequency when the observer is receding from a stationary source in motion. Let us consider a source as a speaker. Suppose it is emitting a sound of some frequency n. Suppose the observer is also at rest. Then, if v is the speed of sound, n waves will occupy the length v. And the wavelength lambda is equal to v by n. Wavelength is the distance occupied by one wave. Distance occupied by n waves is v, then the distance occupied by one wave lambda is equal to v by n. If the source is in motion towards the observer, when the source is moving towards the observer with the speed vs, then in 1 second n waves will be emitted, but these n waves will be occupied over a distance v minus vs. The distance of the speaker from the observer becomes v minus vs after 1 second. Hence, n waves, they crowded together and they occupy the distance v minus vs. So, the modified wavelength of this wave, lambda prime, is equal to v minus vs by n. V minus vs by n is the modified wavelength of this wave. Because the wavelength is decreasing, the frequency increases. So the modified wavelength, the change in wavelength is lambda minus lambda prime, that is v by n minus v minus. Let us consider the case of source approaching and the observer is at rest. The distance occupied by n waves is v, hence the wavelength lambda is v by n. After 1 second, the distance between the source and the observer becomes v minus vs. So, the wavelength lambda prime is v minus vs by n. Since n waves will occupy the distance v minus vs. So, the new frequency, the frequency noticed by the observer will be v by lambda prime. V by lambda prime is the new frequency noticed by the observer. But lambda prime is v minus vs by n. Substituting, we will get v divided by v minus vs by n, that is equal to V by V minus Vs whole multiplied by n. V by V minus Vs whole multiplied by n. This is the relation that is to be used for finding the apparent frequency when the observer is at rest and the source is moving towards the observer. Now let us proceed to consider the case in which the source is moving away from the observer. Suppose the source is at the left and it is emitting the frequency n and moving to the left with a speed Vs, and the observer is at the right at a distance V from the source originally. Then the wavelength lambda is n by V. After 1 second, the distance between the source and the observer becomes V plus Vs. It increases. The number of waves emitted in 1 second is only n. So these n waves will spread over the distance V plus Vs. So the wavelength of the wave lambda prime will be equal to n by V plus Vs. So the apparent frequency noticed by the observer will be equal to n prime is equal to V by lambda prime. N prime will be equal to V by lambda prime because the speed of the wave is V and its wavelength is lambda prime. Substituting the value of lambda prime, we get n prime is equal to V by lambda prime is equal to V divided by V plus Vs by n. V divided by V plus Vs divided by n, that is equal to V divided by V plus Vs whole multiplied by n. V divided by V plus Vs whole multiplied by n. This is the relation for apparent frequency when the source is receding from the observer. Let us proceed to find the apparent frequency when the observer is in motion and the source is at rest. Let us take the case of the old source in which it is emitting n waves in 1 second. Now the observer is at a distance V from the source. Then the number of waves between the observer and source will be n. The number of waves between the observer and source is n. So n waves are situated over a distance V. The number of waves situated in unit length in a distance V, the number of waves is n. In unit length, the number of waves will be n by V. Then let us take the case after 1 second. In 1 second, the observer moves towards the source by a distance V naught. The observer moves by a distance V naught towards the source. The number of waves situated over this distance V naught is n by V into V naught, because n by V is the number of waves situated in unit length. So in a length V naught, the number of waves situated is n by V into V naught. If the source is at rest and the observer is also at rest, he receives n waves. Because of the motion of the observer, the number of extra waves that are received by the observer is n by V into V naught. N by V into V naught will be the waves, number of waves received by the observer due to his motion. So the total number of waves received by the observer is n plus n by V into V naught. N plus n by V into V naught. This is the relation used for calculating the apparent frequency when the observer approaches the source. Let us take the case in which the observer is receding. If the observer is receding, then in 1 second he moves away from the source by a distance v naught. The number of waves situated in the distance v naught is determined as n by v into v naught. Because he moves away from the observer, from the source, he fails to receive the n by v into v naught waves, the number of waves situated over the length v naught. They will fail to reach the observer. Hence, the total number of waves received by the observer will be less than n. So, the number of waves received by the observer will be n minus n by v into v naught. N minus n by v into v naught. This is the relation for apparent frequency when the observer is receding from effect of the motion of the medium. Effect of the motion of the medium on the apparent frequency. When the medium is moving with a speed w, the resultant speed of the sound will be v plus w if the medium is moving in the direction of propagation of the sound. If the medium is moving in the direction of propagation of the sound, then the speed of sound becomes v plus w. If the medium is moving opposite to the direction of motion of the sound, then the speed of sound becomes v minus w. So v minus w will be the effective speed of sound if the motion of medium is opposite to that of the sound. If the motion of the medium is in the direction of the sound wave, then the effective speed will be v plus w. If the medium is moving, relations for apparent frequencies when the medium is moving in the direction of propagation of sound. Relations for apparent frequencies when the medium is moving in the direction of propagation of sound. If the source is approaching a stationary observer, the relation is n prime is equal to v plus w divided by v plus w minus vs whole multiplied by n. V plus w divided by v plus w minus vs whole multiplied by n. If the source is receding from a stationary observer, the relation is n prime is equal to v plus w divided by v plus w plus vs whole multiplied by n. If the observer is approaching a stationary source, the relation is n prime is equal to v plus w plus v naught divided by v plus w into n. N prime is equal to v plus w plus v naught by v plus w whole multiplied by n. If the observer is receding from a stationary source, the relation is n prime is equal to v plus w minus v naught divided by v plus w whole multiplied by n. V plus w minus v naught by v plus w whole multiplied by n. When the medium is moving opposite to the direction of propagation of sound, that is, if air is blowing opposite to the direction of propagation of sound, we use v minus w instead of v plus w. If the medium is moving opposite to the direction of propagation of sound. The case of both source and observer are in motion. If the source is approaching the observer at rest, then the apparent frequency of sound noticed by the observer is n prime, given by n prime is equal to v by v minus vs into n. In case of source approaching a stationary observer, the apparent frequency n prime is v by v minus vs into n. If the observer is also approaching the source, if the observer is also approaching the source, the apparent frequency noticed by the observer becomes n double prime is equal to v plus v naught by v multiplied by n prime. N double prime is equal to v plus v naught by v whole multiplied by n prime. We used n prime instead of n in the case of observer approaching the source. Substituting the value of n prime, we get n double prime is equal to v plus v naught divided by v minus vs whole multiplied by n. Substituting the value of n prime, we get n double prime is equal to v plus v naught by v minus vs whole multiplied by n. If both are receding from one another, then the relation for apparent frequency is n double prime is equal to v minus v naught divided by v plus vs whole multiplied by n. V minus v naught by v plus vs whole multiplied by n is the relation when both. The general relation for Doppler effect is given as follows. N double prime is equal to v plus or minus w plus or minus v naught divided by v plus or minus w plus or minus vs whole multiplied by n. The generalized form of Doppler effect relation is n double prime is equal to v plus or minus w plus or minus v naught divided by v plus or minus w plus or minus vs whole multiplied by n. We can deduce the relation for any case of Doppler effect from this generalized form. We can deduce the relation for any case of Doppler effect. We take plus sign for w. If the wind is blowing in the direction of propagation of sound. If the medium is moving in the direction of propagation of sound, we assign plus sign for w. V naught is taken positive if the observer is approaching the source. Vs is taken positive if the source is receding from the observer. By applying these concepts, we can obtain the relation for any case of Doppler effect. Application of Doppler effect. This effect is used in accurate navigation of aircraft, and it is the basis of accurate target bombing technique. The speed of an automobile can be determined using this principle. Velocities of stars are determined relative to the Earth. This principle is used in tracking artificial satellites. The rotation of Saturn's rings and of double stars has been determined using this principle. This effect is used in accurate navigation of aircraft, and it is the basis of accurate target bombing technique. The speed of an automobile can be determined using this principle. Velocities of stars are determined relative to the Earth. This principle is used in tracking the artificial satellites. The rotation of Saturn's rings and of double stars has been determined using this principle. Summary of this class. The apparent change in frequency noticed by the observer due to the relative motion between the source and the observer is known as Doppler effect. The frequency increases if either the source approaches or the observer approaches. The apparent frequency will be more in case the source is approaching or the observer is approaching. The apparent frequency is less, it decreases if the source recedes or the observer recedes. The wavelength lambda decreases in case of the source approaching. If the source is approaching, the wavelength decreases. If the source is receding, the wavelength observed by the observer will increase. Lambda increases if source recedes, lambda decreases if source approaches. There will be no change in wavelength due to the motion of the observer. Due to the motion of the observer, there will be no change in the wavelength of the wave emitted by the source. The speed of sound depends on the speed and direction of flow of the medium. If air is moving in the direction of the speed, then the speed of sound will increase. If air is blowing opposite to the direction of the motion of the sound, then the speed of sound decreases. So it depends on the magnitude of the speed as well as the direction of flow of the medium. This phenomenon is used in the navigation of aircraft, in tracking satellites, for finding the double stars, etc.